Hello students, in this video let's start chapter 3 of graph theory, that is Euler and Hamilton path. Euler and Hamilton path. The Swiss mathematician Leonhard Euler made the first use of graph theory in 1736 to solve the well-known Königsberg's problem. Königsberg's problem is one of the unsolved problem till today. It is also known as a seven bridge problem. Okay, when this problem is represented using graphs, the problem reduced to the question that can we travel along the, how does the graph of that problem, the graph of that problem is as here the vertices. Okay, this one, these are what edges here. Here let it be A, B, C and D. We have to go from A to D here, but can we travel along the edges of the graph starting at a vertex and returning to it by traveling each edge of the graph exactly once? A similar other question, can we travel along the edges of the graph starting at a vertex and returning to it while visiting each and every vertex of the graph exactly once? So in this chapter we will study these questions which give rise to this Euler and Hamilton circuits. The chapter concludes with the applications of traveling salesman problem and Chinese postman problem. So let's see the definition of Euler path and Euler circuit. Euler path and Euler circuit. So definition: an Euler circuit in a graph G is a simple circuit containing every edge of G. Next definition: an Euler path in a graph G is simple path containing every edge of G. If it will be a circuit containing every edge of G, then it is Euler circuit, and if it will be a path containing every edge of G, it is Euler path. Then the next definition: a graph G which have an Euler circuit is called an Eulerian graph. It is called an Eulerian graph. That is same as to say, if we can travel along the edges of the graph starting at a vertex and returning to it by traveling each edge of the graph exactly once, then the graph is known as Eulerian graph. That is if we travel along the edges of the graph starting at a vertex and returning to it by traveling each edge of the graph exactly once, then it is an Eulerian graph. It is an Eulerian graph. Now let me give two theorems to check the graph is Eulerian or not. Okay. Theorem 1 is about Eulerian graph. A connected graph G is Eulerian if and only if the degree of every vertex is what? Even. If and only if the degree of every vertex is even. For example, here, suppose these are the vertices. So check, each and every vertex have an even degree. So it is an Eulerian graph. Theorem 2 is about the Euler path. A connected graph G has an Euler path if and only if it has exactly two vertices of odd degree. For example, it has an Euler path. It don't have an Euler circuit. So it is not an Eulerian graph, but it contains Euler path. Okay. Now what about this? if the graph is as such, now here the degree is 2, here degree 3, 3, 3, 3. So 4 vertices of degree 3. Now neither all vertices are of degree having degree even, and nor only 2 vertices, exactly 2 vertices of odd degree, 4 vertices of odd degree. So this is, or it is neither contains an Euler circuit nor an Euler path. As such we can write for that. Now once again we will come to the Königsberg's problem, that is 7-bridge problem, whatever the figure initially I taught you. If you look for that one, let me draw that figure once again. This is the figure for Königsberg's problem. Look at it. Here degree 3. Here the degree is how much? 5. 3 and 3. So all vertices of degree means it is not even. It is odd. So it doesn't have an Euler path. So no question about Euler circuit also. It doesn't have an Euler circuit. So it is not possible to travel across all these. These are nothing but the bridges. All these bridges exactly once and return to the starting point. Actually, what does this problem? This problem is the city of Königsberg, Prussia, now called Kaliningrad, and part of Russian Republic, was divided into 4 sections by the branches of Prigel River. 4 sections, 1, 2, 3, 4. As such, it will be divided. These are what the branches of that Prigel River. These 4 sections included the 2 regions of the banks of the Prigel and Neef of Iceland, and the region between the 2 branches of Prigel. Okay, these regions are linked by 7 bridges. These are all 7 bridges. Okay, but here it doesn't possible that we will travel across all bridges exactly once and return to the starting point. It is not possible here. Okay, that is the Königsberg's problem or 7-bridge problem. Okay, now the next part we have to see the Fluoresce algorithm. If the graph contains Euler circuit, means what? Each degree of each vertex is what? Even. Then we can find that Euler circuit using this Fluoresce algorithm. What are the steps for that one? We will write and then we will solve examples on them. Okay. Fluoresce algorithm, as I say, if the graph contains an Euler circuit that is degree of each vertex is even, then we can use this Fluoresce algorithm to find the Euler circuit. Okay, in this algorithm this algorithm, we start with any vertex of G, and go on tracing the edges of G one by one. While tracing the edges, we use the rules. First rule, erase the edge which is traversed. Second, erase the isolated vertex if any. Then again, traverse the bridge. Only when there is no alternative. Okay. Finally, we reach to a single vertex. That is also erased. The edges traced in order to give the Euler circuit. In G. Euler circuit in G. Let's solve example on this so that you will be very clear for this. The question says that find the Euler circuit in a graph given below using Fluoresce algorithm. This graph is given to us. Vertex V1, V2, V3, V4, V5, V6, and these edges are there. Okay. So now let's check the degree. Here degree 2. What about degree 4? Here the degree 4, then 2, 4 and 2. So all vertices are of even degree. So the graph contains the Euler circuit. This is final. So solution. Since the degree of each vertex is even, this graph has an Euler circuit, or it contains the Euler circuit. It's okay. Fine. Now step. Let's write step. Remaining graph and edges traced. Let's do this. So now step 1, suppose I will start from V1. Start at V1 and trace the edge E1. Start at V1 and trace edge E1. Okay. So due to that, what happened? Remaining graph. So except E1 we have to draw the graph. Yeah. We want to draw E1 only. This is V1, V2, V3, V4, V5 and V6. V2 to V6, this is E8, right? This is E9, then E4, then E7, this is E6 as it is, this is E2 as it is, this is E3 as it is, and this one E5. This is our remaining graph. And the edges traced. Which edges we have traced? From V1 to V2. That is what? E1. Right? This edge we have been traced. This is our step 1. Now next step. Trace. From V1 we can trace. From E1 we can trace E8. We reach to V2. So we can go further. So trace E8. So the remaining graph is remaining graph will be this. You can give names to that one. Yeah. Here V1, V2, V3, V6, sorry, V6, V5, V4, V3, right? So this is E2, E3, okay, then E5, E4, E7, E6 and E9. Now which edges we have been traced now? E8, right? First V1 to V2 there is E1. This is from V1 to V2. And now this E8 to it is up to V6, right? Now after this, next step, trace, we reach to V6, so trace E9. Trace E9. After tracing E9, we get V6 is isolated. Look at this. V2, V5, V3, V4. So we get these edges only. Right? This is V1, V2, V6. Then V5. Here V4, V3. Okay. The edges are left. Which one? E2, E6, E7, E5. This is E4. This is E3. Now we have been traced E9. So V1 to V2. That is edge E1. V2 to V6. Edge E8. And V6 to V5. It is edge E9, right? These one we have been traced. But now this is an isolated vertex. So what the rule says, we have to erase the isolated vertex. So erase. Here the step says erase V6. Erase V6. So due to that, this graph will become simply except this V6 we have to draw. So V1, let me write this one here. Step remaining graph and edges traced. So what are the steps we have now? Erase V6, right? So what is the graph that time? V1, V2, V5, V3, V4, right? So V1, V3, V4, V5, V6, sorry, V2. So the edges are what? This one, E2, E3, E4, this one, E5, this is E6, E7. Now this edges traced are as it is, just like a previous one. Here V1 to V2, V2 to V6 and V6 to V5. This is E1, V6, this is E8, this is E9. Okay, this is our next step here. Now once we reach to V5, we can, from V5 we can go here, but we can go here, then as such also. Okay, fine. Or we can go from this E4 as such also. So what will be the next step? Let it be trace E4. Trace E4. So this E4 we have to trace. So we have to reach to V4. So we will draw a graph except this. V1, V2, V4, V5, V2. This is V3. So these edges are left there. E4 is not traced now. This is E2, this is E3, E5. We will eliminate that one from original graph while tracing. So what is here? V1 to V2 to V6 to V9, then V5, right? V5, sorry, V4. V1, V2, V6, V5 and V4. So it is E1, this is E8, E9 and E4. This one we have been did till, right? The next one is what? Trace E3. Trace E3. After tracing E3, what happened? V4 will become isolated. Right? This is left. So V1, V3, V4, V5, V2, E2, E6, E7, E5. Tracing V1 to V2 to V6 to V5, V4 to V3. V1, V2, V6, V5, V4 and V3. So these we reach till this E3, this is E4, this this is E9, E8, and this is E1. Okay, now the next step says erase V4. So let me rub this part, which is not required now. So step remaining graph and what edges traced. So here we have to erase V4, it is isolated. So erase V4 first. So what is the remaining graph is simply this part. So V1 to V3, V2 is here, V5 is here. V1, V3, V5 and V4, right? This is E2, this is E6, E7 and then E5. So here the same one, V1 to V2 to V6, V5, V4, V3. E1, E8, E9, E9, E4 and this is what E3. Now we reach till this. Now we go to V3 yet, right? From V3 we can go to V1, but these edges are left, so let's go to V5. Okay, so trace E5, I can say trace E5. Okay, so what is here? V1, V3, V4, V5. These are left only. V1, V3, V4, V5. So E2, E6 and what? E7. So what is here? V1 to V2, V6, V5, V4, V3. So V1, so this is E1, this is E8, then E9, then E4, E3 and what? E5, right? These one we have been traced. Now we reach here. So now trace E7. E7. So while tracing E7, what happened? V5 will become isolated. Right? So what is here? V1, V2, V6, V5, V4, V3. So we have, this is E1, E8, E9, E4, E3, this is E5 and this is what? E7, right? E7. Okay, so now erase V5. erase V5. So erasing V5, here we get this one, V1, V3, V4. This is E2, E6 only. This is same as above. Same as above we can say. Okay. Next step remaining graph. And edge is traced. What is it further? Now we reach here. So trace E6. Trace E6. What we get? Simply due to that V1, V3, V2. It will be V2, right? It is V2. From here I have made a mistake. So check it wherever we have made a mistake. It is V2. Right? This is V2. So here it is E2. If we want to draw E6, we have to trace E6. So here V1, V2, V6, V4, V5, V4, V3. So V1, V6, this. As such we are going. We reach here, right? V1, V2, this is V6, V5, V4, V3. This is E1, E8, E9, E4, E3, then E5, E7, and then E6. Now so again this V2 becomes isolated. So erase V2. Erase V2. So here this V1 to V3, this edge E2 is left only. This is same as above. Okay. So what is the next? Trace E2. Trace E2. So here tracing E2, what is left? V1 only. V1 will left here, right? So here as such V1, V2, V6, V5, V4, V3. So E1, E8, E9, E4, E3, E5, E7, E6 and E2. So lastly erase V1. So nothing is left here. Here same as above, right? So this is a completion of this algorithm. So what does the Euler circuit we get? Euler circuit is, as we go right down the same path, is what? V1, then E1, V2, E8, then V6, E9, then V5, E4, V4, E3, V3, E5, V5, E7, V2, E6, V3, right? E6, V3, E2 and then V1. This is our Euler circuit here. As such, we have to find the Euler circuit from the given graph. Okay. Now here we will stop. In next video we will take the example on this one again. Thank you.